Thank you for having me. So yeah, this is a combinatorial talk. So
Yay!
Our friend matroids polynomials term. But if you know a little bit about tropical geometry, then you know that matroids counter-rising from tropicalizing linear spaces. So this is actually about linear spaces. So I will talk about this longest paper I've ever written. It's over 100 pages long. So therefore I cannot cover all details, but I will try to tell you the main ideas, the combinatorial concepts you need, the new language or the new things we introduced in the paper, and then hopefully I have enough time to give you as many examples as possible. Okay, so let's get started with what is a matroid. A matroid is a generalization of the concept of independentness, or dependentness, whatever you prefer. So as you are used to from at least linear algebra, there are bases, and now we want to have a combinatorial description. So we forget about vectors, but we say a K subset of a fixed n-element set. Set of bases of a matroid if the following exchange property is satisfied. So whenever you have two bases and take an element of one of the bases, you can find another element in the second basis, such that if you replace I with J, it is a basis there. So this is what you learned in linear algebra as to find its exchange property. And as you are used to, all the terms are actually the ones that you're used to from linear algebra. So we can talk about the rank. This is just the size of independent elements. A maximal independent set is the basis. And yes, just count this. And what are examples for matroids? Of course, you can just claim that every K element set is a basis. That will give you a matroid. That's actually a pretty interesting one. It's the largest one for given n and k. This is called the uniform matroid. But then, as I told you, so things are coming from linear algebra. So you can also start with finite number of vectors in space. So, for example, the columns of this matrix, and then consider which of the columns are independent, and that gives you the basis of a matroid. And if you're a little bit careful, then you will figure out with this particular example, column 3, 5, and 6. They might be dependent, might be independent. That actually depends on your field or the characteristic of your field. So if your characteristic is 2, then they are dependent, and otherwise they are not. So in the picture, you get the final plane where you have these 3 points on the line or not. And this actually already shows you that if you play a little bit around with this and use it as a toy, then you can somehow enforce the characteristic. So this, depending on if this is dependent or not, you force the characteristic of your field, and then of course you can have something where you force the characteristic to be 2, but at the same time to be not 2, and then you get something which is not representable, so it's not coming from a vector space. So the truth is almost nothing comes from vector spaces, but gives you the right application. Combinatorially, there's much more. Okay, so this is what a matroid is, or one way to define them. There are many other ways to define matroids, and there are many other terms. I cannot even go through all of them, but here are 3 important ones. So if there are bases, these are the maximal independent set, then I can also talk about the minimal dependent sets. They are called circuits. These would give you a different description of the matroid. I can talk about closed sets. They are called, for a traditional reason, flats. This means these are the maximal sets such that whenever you add an element, you would increase the rank. So in this sense, they are closed. And then there's something which might be a little bit less common, but very nice, so-called cyclic flats. So these are very special flats. These are the flats which you get by taking the union of circuits. Okay, so here's a little example. This is not the same example as before, but so if you look at this example, the set of flats I have written here, and I have written it in a way that you see how the sets are included in one each other. So this gives you a lattice. And then if you want to see what are the cyclic flats, I circle them with a red. So there are how many? 5 cyclic flats. And for example, this 1, 2, 3, 4 itself is not a circuit. So 3, 5, 6 would be a circuit. You can easily check here. But 1, 2, 3, 4 is not. But it's the union of 1, 3, 4 and 2, 3, 4, which are circuits. So therefore, it's also a cyclic flat. Okay, so these are the combinatorial terms that we need. And I promised you some polytopes. So let's jump into that. So how can I turn a matroid into a polytope? There's a standard way, and there are actually many polytopes I could associate coming from the different definitions, but I started with the basis, so I want to introduce the base polytope, or just the matroid polytope. And what do? I take every basis, I look at the characteristic vector, so it is a vector in n-dimensional space, and I write the 0 if an element is not there, and the 1 if the element is in the basis. So for every basis, I get a vector this way, a 0, 1 vector. I take the convex power of all these vectors, and that gives me my polytope. If I do that for the uniform matroid, I get actually a famous polytope. It has very nice combinatorial properties, which is called the hyperspace. And then every other matroid polytope is a subpolytope of this. How do I get the others? I mean, either I play the same game as before, or dually, so I can also describe it by inequalities. I take my hypersimplex and I cut away vertices and points with these inequalities, where, I mean, this inequality depends exactly on the cyclic flats. Therefore, the term is pretty nice if you want to study matroids via polytopes.
But do I need all of, are these all defining gradients then?
No, not all of them are facet defining.
Okay.
So there might be redundant.
But can I leave out cyclic? Is the statement still true, or does it?
Yes, and yeah, I mean, then you just added more unnecessary inequalities.
Okay.
But the statement is still true, yes. But you can't drop the word flat. So if you just look at circuits, then you get something which is too large. And then you have to take the integer all of what you got, and that will define that. It's nicer to have fewer inequalities. Okay, so here's an example, right? So this is a toy example. It will appear all over this talk. So this is n, so I have 4 elements, 1, 2, 3, and 4, corresponding to the 4 columns of this matrix. And as you see, this is not corresponding to the uniform matroid, which would be an octahedron. But fortunately or unfortunately, the last 2 columns are clearly dependent on each other. So 3, 4 is not a basis in this case. So therefore, the matroid polytope will be just this Egyptian pyramid. And I have to cut away this, this vertex or this point. How do I do this, or how do I see this? Okay, so this is the inequality. X3 plus X4 is smaller than 1 because 3, 4 will be a cyclic flat operator. So this cuts away exactly the point 4, actually all the points here. Okay, so this is polytopes. And now we're getting to new terms. So these are things that I introduced with my co-author years ago. So we call the following set Cusps. So these are all the sets of size k, which are subsets again of my large set n, so which is called the ground set. But this time I want that the intersection of this set with given set A is larger than the rank of this set. Okay, so where does this come from? It's roughly speaking coming from these types of inequalities. By now I flip the sign, right? So
why call it Cusps?
It was not my decision, but I mean,
Okay.
it looks like a cusp over this
Okay.
this piece here, but it's not an algebraic term.
Okay.
Yes, but yeah. So I mean, the only interest, or the most interesting part here is that all the elements here are never bases, right? So they have the right size. They potentially could be, but then this condition here ensures they are not. Okay. And then the other term we need is being stressed. Another nice name. I can actually explain where this comes from, and we will see in a couple of minutes. And we call the set stress when the restriction, so this is this subset, so the restriction of a matroid is again a matroid, and the bases look like this. So these are all the subsets of A, which are independent in A, so A is of rank R, and these are all the R subsets such that the rank is maximum. So if this set happens to be a uniform matroid, then this is nice. So I have not excluded any of these members, so therefore this will be another hypersimplex if I take the convex half. And the same holds true here, but this is just a dual picture. And I can see this nice property of being stressed best in the lattice of cyclic flat or the lattice of flats. How do I see this? So I look at a set, let's say a closed set, flat. So for example, set 3, 5, 6 over here, and then I look at the lattice below from the empty set up there. This looks like a uniform matroid. And also the upper part, so from here to there, this looks also like a uniform matroid. So this would be the stressed set. So 3, 5, 6 is stressed, but for example, 1, 2, 3, 4 is not, because if I look below, then there is something dependent here. And the other way around, 1, 2 is also not a stressed set, because if I look above, this thing here, this piece there, doesn't have the correct uniform. Okay, so these are the two terms we need. So what can we do with them? So this is why the word stress belongs here. So if I have a matroid and I can find the stressed subset, then adding this stressed subset, or the cusp of the stressed subset, to my original set of bases gives me a new matroid. This matroid is called the relaxation M by A. And yeah, so this way we can enlarge the original matroid. And the word relaxation comes from optimization, where we relax one of these facets of inequalities. So what happens for our toy example? So let's start with the uniform matroid, which is the direct sum of these two pieces. So in other words, it's just a square. If I want to relax 1, 2, then I remove the inequality, which cuts away 1, 2, and I get my Egyptian pyramid. Or if I relax afterwards 3, 4, then I get the full dirty tree. So this is how it works. And now, why is relaxation nice? Because relaxation describes many new matroids given one. And a particular interesting class of matroids are paving matroids. Matroid is paving if each circuit is of size k or k plus 1, where k is the rank of my matroid. Okay, so if you look at this lattice of flats, then all interesting things happen only on the top level. So that top level means everything up to, there's this last node, which is not interesting, and then there's the layer of rank k minus 1 flats, and there all my circuits appear. And it's called sparse paving if this is also true for the dual matrix. So in other words, if each k circuit, each circuit of size k is actually a flat for my paving matrix. So meaning that the cyclic flats belong only, they are just one circuit, not a union of more. So these are nice classes. Why are they in particular interesting? Because there's this conjecture that almost all matroids are sparse paving. So by understanding these matroids, you have understood most of these matroids. And I gave you this reference from 2011, but this conjecture is much older. I think it's from the 70s. And by Water and
Is there numerical evidence for it as well? If people just try to compute
yes, so it's hard to compute all matroids.
Yeah, I know.
This increases exponentially. Yes, there is evidence. So first of all, you can compute all the matroids, I think, up to 9 elements, and it's clearly shows that it's
Okay.
should be true, but then also if you take the logarithm, so if you take the log of the number of sparse matrices, the sparse paving matroids, the logarithm of the matroids, and you take their quotient and the limit that goes to 1. That is no. This is approved by Don van der Poel and Woody Pellenash. So there is true evidence for this.
Yeah, great.
Okay. And why are paving matroids nice for our game, and why did we pick all these terms? Because there is this nice game, or this nice alternative description of paving matroids. So if I relax all the stressed rank k-1 flats, which are these circuits here, then I get back the uniform matroid. So this, for example, the square here is a paving matroid. And if I relax, first 1, 2, and then 3, 4, or the other way around, then I will get back the uniform matroid, and this proves actually that this was a paving matroid. Okay, so this in mind, we can even generalize the concept and go to what we call elementary split matroids. So a matroid, so this is a theorem because they have a complicated definition, but for this purpose, we can take this as a definition. A matroid is elementary split if and only if, after relaxing all the stressed flats with non-empty cusps, so relaxation actually change something, gives you back the uniform matroid. So this is a nice large class of split matroids, and by the previous result, you see immediately that sparse or even paving matroids are subclass. The original definition goes back to my own PhD thesis, but then there are also excluded minor characterizations of combinatorial classical notation for describing a class of matroids, and then in particular these elementary split matroids. They came out in recent works where they prove a lot of combinatorial properties for them. By now, I think these two authors have at least 4 papers on these classes of matroids. Okay. And here's a nice example. So an example that we call cuspidal matroids. So as in the previous example where we have this product of 2 lines on top of the square, we can take 2 hypersimplicities and their product, and now play the game and relax one of the inequalities, and you get a new matroid polytope. Or if you write in this fashion, you can forget about the polytope. And this kind of polytope we call the cuspidal matroid. And maybe it's interesting to say so. I told you that there's this conjecture that almost all matroids are sparse paving, but we believe that even if you remove all the paving matroids, then almost all the matroids which are left should be elementary split. So this is even an interesting class after removing all the paving.
And almost means all but finitely many, or some limits?
Almost always means in the matroid language that this limit, if you take the limit, the number or the size of the ground set goes to infinity, then it should turn to 1. Okay. Because everything is finite if you fix the grounds with matroids.
That's right.
Okay. So these are the terms we need. And now I can look at the polytopes for a short moment. So how does this look like? So if I have my matroid polytope, so let's say maybe one of these 2 Egyptian pyramids, and I add one of these cuspidal pieces, which in this case is also a pyramid, I will get back the uniform matroid world. I look at this description, the intersection will be the square, and everything behaves nicely. For a higher dimension, which I can't draw correctly, because this is the only 3-dimensional picture I can give you fully. So this would be a 4-dimensional polytope or a projection of a 4-dimensional polytope. Here it can happen that your matroid polytope is this piece here, and then adding a cusp can be either adding this piece or adding that piece. And again, so the intersection is one of these nice pieces here, and you can see actually geometrically what happens if you do this relaxation. So relaxations are actually a combinatorial or a geometric operation. Okay, so now the title is not only matroids, it's large classes, which I think I verified. So there's also the term valuation, and it's not the term valuation that you are used to from tropical geometry. It's a little bit confusing. There are two terms of valuation, one for polytopes and one for, fields or rings. So this is the one for polytopes. So let's consider a family of polytopes and some nice abelian group, then a map from this family to the group, transferring the geometric information into algebraic information, which is called valuation. You take your map for the union of these two polytopes, and also for the intersection gives you back what happens on the polytope or the sum of the two polytopes. And of course, this only makes sense if this union is in this class again, or again a polytope. That's of course not always guaranteed. And again, I also want that the intersection is a polytope. But that's trivial, but if you have a family, that might not happen. So I want that all the pieces which occur here are in a family. If this condition holds for all these four polytopes, then that will be a valuation. Okay, and in our case, so I will, well, for me, these polytopes are either all matroid polytopes on a given fixed ground set, or just a union of all these possibilities. This is my setting. But if you go one floor up, the people there study valuations for convex bodies, then of course they have very different settings here. Okay, why are these valuations nice? Because they live in particular nicely with these elementary split matroids. So if I have an elementary split matroid of some rank and some cardinality, so let's say rank K and cardinality N, then I can express the valuation on that matroid by evaluating only three different types of matroid. The uniform matroid, okay, these cuspal matroids, and then direct sums of uniform matroids. So which is pretty nice because there are very many of these elementary split matroids. They can be complicated, but then this formula tells you if you want to figure out what this valuation is, you just need to understand these three types.
What is the big lambda?
This big lambda is a cuspal matroid.
It depends on R, K, H,
And
and
it depends on R, K, H, and S. So what are, so R is the rank of your, so this depends, okay, so it depends on N, which is the size of your ground set, and K, which is the rank of your matroid. That's maybe nice. And what are these R and H? So you have always the stressed set that you want to relax. The rank of that stressed set should be R, and the size should be H. So they have to record all these information. So we'll go back to what's a cuspal matroid. It's the relaxation of this thing here, and that depends really on H and R, which is if you want to the rank, the size of your stress subset. And therefore, I can compute how many are there of this particular, how many stress subsets of size H and rank R are there, and then this gives me the form. Okay, so let's go to some examples. Maybe the first very trivial example, at least to see that this is a valuation, right? So this condition will be satisfied by any measure. That's what you probably learned at some point. So the volume will be an example. And we can immediately apply it. So the nice thing, I haven't mentioned that before, but the uniform matroid is also a particular type of these cuspal matroids. So it even reduces the work. And as you might know, right? So the matroid polytope of this piece is a product, so it's lower dimension. I can drop it, and therefore I just need to understand what happens on cuspal matroids. And this can be counted, for example, by counting permutations where the number of V senses is given by the rank minus. If I do so, then I can, using this theorem, write down a nice compact formula. If I apply it, for example, to sparse paving matroids, I immediately recover one of the 3 theorems of Asherov's paper. So it's roughly speaking for free. Get results of that type. Another, standard example for evaluation is the Ehrhart polynomial. So what is that? So that counts the number of integer points of dilations of your polytope. Again, it's obvious that this is evaluation because every point which is in the union and not in the intersection is counted once, so it must be in one of the 2 polytopes, or if it's in both, it must be in both polytopes, or if it's also in the intersection. So therefore, this is clearly evaluation. This is, there's a field where in mathematics, an area where they love to study these Ehrhart polynomials, and people in there conjectured actually a lot about this polynomial. Among these conjecture were that if you look at the Ehrhart polynomials of matroid polytopes, then the coefficients are always positive. And my co-author recently showed this is not true. And these techniques that we demonstrate in this paper allow you to prove this quite easily. So,
did you find an example, or was it just
sort of an example? Sort of an example. Okay. So here's the strategy, right? So find a formula for the Ehrhart polynomial of the uniform matroid. Okay, that was done already. Find a formula for these Cusps matroids, which are of a very particular form. Right here you see H is of, the size of the set is exactly K again, and the rank is K minus 1. So it's very, very specific form, but this is what belongs to being sparse paving. So we just need to find these 2 formulas, and then there's the trick. You need to find this lambda, right? So this lambda, which depends on the rank and the or R and H, but here I omitted that, and find how many of these sets can I find, how many of these circuits are in the matroid. And luckily, there's a nice bound for it, and this tells you there is a matroid with that many stress cyclic flats. And once you know that, you can say, okay, there must be a matroid polytope, a sparse paving matroid polytope, which has a negative coefficient by just applying the formula again. So in this sense, it is somehow not a really complete true example, because I don't tell you how I have to distribute these specific flats. So, and of course, I cannot write down. I haven't written down numbers here, but I think for rank 3, I think you need maybe something like 3,000, 4,000 of these cyclic flats. That's a matrix I can't write down. No, that's not true. Not cyclic flat, but n is, I think n is equal to 3,000 or 4,000. So matrix I never can write down. Okay, and just for completeness, if your rank is very small or pretty large compared to the number of elements, then the conjecture holds true. That's the result that I proved that Louis Caroni and Caroni and Okay, so these are the examples from, I would say, polyhedral geometry, and then there are more examples. So this is a classical example from matroid theory, and let me tell you how to construct these valuations. So typically it's in matroid, so for matroid invariants or matroid functions, it's not so clear if they're valuations or not. So we need some tools to prove this. And the best and nicest tool I know is by Adila and Sanchez. So they tell you if you have already 2 valuations, then you can get a new one by just producing a convolution of your previous ones. And it's just a convolution. So you take the restrictions here and the constructions there, build in valuations. That might be, in the first glance, look a little bit ugly, but it's very, very useful. So for example, if I just assign to every matroid -1, n prime and k prime here are fixed, right? So the rank and size are fixed. So this is the constant, or I assign just the parameter -t, then these are clearly valuations, at least with the definition I gave you. And then I can use this trick and plug it in, and I get something which might look complicated, but this is the characteristic polynomial, so a standard matroid invariant of a of the polytope. And I titled this Whitney numbers of the first kind because the coefficients here are Whitney numbers of the first kind. Okay, so this is a way to construct a population. Let me just tell you that also the Whitney numbers of the second kind, which count the number of flats given by their ranks, is another valuative invariant. With our techniques, you can even get the formula. And I think this was last year or 2 years ago, June and co-authors proved that the first coefficients, the first half is increasing, and they are top heavy, meaning that Wi is smaller than Wk minus I for I between 0 and k half. But it's not clear if this is a unimodular sequence, meaning that it only has a peak in the middle, who knows, or if it's log concave, which is also a nice property that people care about combinatorics. Okay, so these are two standardly matroid invariants, I would say. And here is one that I would associate to algebra. So given a matroid, I might can construct this Chow ring of the matroid. And this is an honest Chow ring if the matroid is realizable, but otherwise it's not. And here's the definition. So for every flat, I introduce a variable, and then I have to quotient out two ideals. So one's given by incomparable flats. So if they are not contained in each other, then their product should vanish. Or if I have a fixed element I and a fixed element j, and I take all the flats which contain I and all the flats which contain j, then their difference should also vanish. Don't want to distinctions. Therefore, I quotient out by these two ideals, and this is my Chow. Okay, so I won't give that extra talk, which is written in these two lines. So, why are Chow rings of matroids interesting? Because they satisfy the Kähler package or Hodge-Riemann relations, Poincaré duality, things like this. And then you can use this, for example, and that's actually a very famous group, right, to prove the log concavity of the coefficients of the characteristic polynomial. So the Whitney numbers first time. Okay, but that would be an entire talk, just having to know how this really works. But there is a nice relation between our matroid valuations and this Chow ring, naming there's a valuation that I can write down explicitly or kind of explicitly from the matroid polytopes, or yeah, because I define this or matroids itself to the Chow ring of the free matroid, so where the rank is equal to this ground set, or for the experts. So this is the permutation variety, or the Chow ring of the permutation variety, I should say. That I've written here. So this is a realizable case. And so once I fix that, then I can express any other valuative invariant, which has a very small detailed property, meaning that it vanishes for matroids where you have loops, and therefore, I mean, if you look at all these papers where these Chow rings of matroids appear, there's always the condition that the matroids should have no loops. So this is encoded here. Then I can find a homomorphism from this Chow ring into my group, such that this or my original valuation factors through this homomorphism.
Can you evaluate the notation of the n factor n factor n? I will just say what this means.
Yes, okay. So these are all the matroids where the ground set is fixed and of size n. And these are just okay. Actually, if I see this correctly, there's the n missing here.
Okay, so both missing.
Yeah, both of them should be for fixed ground set size. Otherwise, you should have taken the product here of all the Chow rings. Okay. And the other way around, this is always true. So this is the only interesting direction. So if I have the homomorphism, then of course I can first apply this nice valuation, then the homomorphism, and that will be automatically a valuation. So that is a trivial case. So somehow the Chow ring or homomorphisms of the Chow ring are in some sense equivalent to studying valuations.
In the tropical language, does that send a matroid to its Bergman fan?
Ah, yes. So you could consider, I mean, so instead of the matroid polytope, the way I phrased it, you could consider the Bergman fan, or in general, for every tropical variety, you can do this. So instead of the polytope, you take the dual and pick the correct places. And here it's the Bergman fan, and then yes, everything works as you're used to. So this map actually here is defined by the product, because this is a ring, you have a product, and the product is just the matroid intersection, or if you like and prefer, it's the tropical intersection, the stable tropical intersection of the Bergman. So all the tropical geometries are called expansion. And if you want to learn and see a little bit more about this particular ring, then there's this work of Simon Hampe, who explains how this works and how this is related to matroids. And then there's a continuation, I would say, by Spencer Fettman, CRISPR, and Simpson Connor, who tell you how to do it if you don't have the free matroid, which then is just a quotient in this case. So therefore, always this homomorphism property applies. Okay, so there's another nice algebraic property, right? So this Chow ring is actually a graded ring. Its gradient just comes from the polynomials I can write down here. I factor through two homogeneous ideals, so therefore everything is fine. This gives you a graded ring. And once you have a graded ring, you can ask for the Hilbert-Poincaré series of that. So I'm not doing this, and then in this case, it's a finite degree, and therefore it's just a polynomial. And it's not a surprise in this talk that the map, if you start with a matroid and you go to this matroid Chow ring of this particular geometry, this gives you a Hilbert polynomial, and this is again a Valuative invariant. So everything is nice. We can even say that this polynomial is polytromic. So if you read from the top or the bottom, so the highest degree term is the same as the constant, the coefficient of the highest degree term. It's the same as the one of constant term, and when you go further in, it reads the same. And we already know this. They form a unimodal sequence, so they go up to the middle and then down again. And what is open, right? So we have people in combinatorics, especially those which are interested in these matroidal questions, they ask themselves, are these do these sequences form log concave sequences? Or even stronger, so something which would imply that these are log concave, is that the polynomial, the Hilbert-Poincaré polynomial, is a real rooted polynomial. So we don't know, but all the Hilbert-Poincaré polynomials we look at were actually real rooted.
This would imply
that implies log concavity and also a modularity.
Valuative invariant, one of the ones that is zero when the matrix has loops.
Yes, I mean, actually, so this Chow ring is not defined as loops.
I mean, it's only defined on the vectors of flats, right? And then
Yes, exactly. That's why the title and the papers often do not talk about matroids, they talk about geometries. Yeah. So you can always assume that M is simple and for sure loop free.
You can apply the theory of the previous section to it.
But I mean, to make this a Valuative invariant, you're right. You should assume that if it has a loop, it is just okay. So let me end with the open problems. So what is to do for you? So it's hard to tell what these numbers lambda RH are. Good bounds, of course, help you to group all these theorems and all the properties. So what I know is that if you have a sparse paving matroid, and you want the maximum number of these stressed subsets, and this is somewhere between 1 over n and choose k, and if you look at the dual or not, therefore the minimum of 1 over k plus 1 times n choose k, or 1 over n minus k plus 1. Okay, so if you can improve this, then I would be very happy, but not only I mean, so this is actually, especially for the sparse paving matroid, an important question in coding theory. So this this would be a really strong result. But then, of course, there's something which is less studied is what if I leave the case of sparse paving matroids and I give you some sequence of these lambdas? Can you tell me if there is an elementary split matroid where the sequence is exactly the sequence or the number of stressed subset of the corresponding size?
You say proposition, this is open or not?
This is known, these bounds.
Okay, then now.
But bounds are known, but maybe you can improve the bounds.
I see, okay.
And the problem is, what if I give you numbers? So I mean, I can tell you.
Okay.
So if this lambda is this number, then I can tell you, or yeah, then I can tell you, yes, there is such a sparse paving matroid. But if you make it a little bit larger, I don't know. Probably really depends on n and k. Actually, I know that this is true. So it's pretty complicated to foresee what this number is for a given. Okay, so let me end here.